Hello, and welcome to Astronomy 100. In this segment, we're going to continue our discussion of the mechanics of the sky. In particular, we're going to talk about apparent motions, how the sky appears to move over time. Now, there are three ways that the sky can appear to move over time. Part of it has to do with the Earth and how it moves, and the other part of it has to do with the other objects that we're looking at. For instance, if you were to go outside and look at the sky for a few minutes each night, you may not believe that the sky is actually physically turning or moving. It looks like everything is sitting still. But in reality, the Earth is turning on its axis. And as the Earth turns on its axis, that can create the illusion that objects are moving across the sky. The other way that the appearance of movement occurs is that the Earth is physically moving in its orbit around the Sun. And so day after day after day, the Earth will make a little bit more in its progress in that orbit, and objects will appear to move. The third way is that the objects themselves can appear to move across the sky because of their own motion. An example would be the Moon. As the Earth turns on its axis, the Moon is of course moving in its orbit around the Earth, and so each and every day or each and every night, the Moon's going to look like it's in a different place. So to get us started, let's look at a video to see how the appearance of movement occurs over time. This video that you see here is a time-lapse video that was taken over the course of an entire night, and this was taken from the country of Chile, and this is a very, very high desert plateau where there are astronomical telescopes set up to observe all night long. In particular, the one that you're looking at is a radio observatory, so it really doesn't matter if it's day or night. And when we click the play button here, what you'll notice is that you're going to see the appearance of the movement of the sky. You'll see some cars coming and going very quickly in the background, and every now and then you'll notice that the radio telescopes are going to reposition to a different place. But watch what happens when we actually play the video here. You'll notice the moon is setting, the sky will become much darker. And as the hours of the night go by, you can see the slow turning of the sky. The Milky Way is coming into view. Everything seems to move collectively together. And if you remember from a previous discussion, we talked about the notion of the celestial sphere, the idea that everything seems to be attached to one sphere that surrounds the Earth is easily understood if you see this video. In reality, there is no celestial sphere, but you can understand the illusion of something that surrounds the Earth that is, of course, what everything of the sky is attached to. The Milky Way passing overhead, getting very low, and then eventually the Milky Way will set and we go back to daylight. So you can see that there is this illusion that the sky has this turning motion to it, but we'll find out in a minute in reality it's the Earth actually turning on its axis. So this is the recreation of that turning or that slow movement of the sky, and this is looking to the north. On the horizon here, this is the imaginary horizon. This would be looking due north. And what I want you to notice is all of the constellation patterns seem to stay together. In other words, the patterns are the same at all times, but they are slowly moving around the sky. And if you look very, very carefully, you'll notice that they all seem to move around one particular point, this point right here. Everything seems to be swirling or pivoting around that point. And if you remember from a previous segment, this point on the sky is the point, if we're looking true north, this is the point that we call the North Celestial Pole, or the North Pole of the sky. So this is the point that everything in the sky appears to turn around. What I want you to notice is there's a star, this star here called Polaris, that is remarkably close to that particular point. Polaris is not exactly on that point, but it's very, very close to that point. And what I want you to notice is, even though we can't see that dot in the sky, we've obviously projected it onto this animation, even though you can't see that dot on the sky, if you want to find that location, you can actually simply use the star Polaris. It's essentially close enough. So Polaris is very, very close to the North Celestial Pole. The word Polaris itself means pole star, or the star at the pole. And it turns out that because of the position of Polaris, it is a very, very important star when it comes to looking at the sky and navigating the surface of the Earth. So what I'm going to do is tell you the couple of things that make the star Polaris so significant. The first thing I want to show you is how to find Polaris. one of the difficulties is that Polaris is not a very bright star, but it is a star that is important in its location, not necessarily its brightness. It is the last star in the tail of the small bear. Remember, Ursa Minor means the small bear. And one way you can find it in the sky is if you can find Ursa Major, or the asterism portion of it called the Big Dipper. You'll notice that if we connect these two stars together and just simply go in a straight line, we go across a fairly empty part of the sky. But the next notable star that we run into is Polaris. So sometimes these are called the pointer stars that help you find the position of Polaris, or point to Polaris. Now, Polaris has a nickname that you've probably heard of before. It is commonly called the North Star. And the reason why it is called the North Star is a very important reason. Let me show you why. Because Polaris is the star that is directly over the north pole of the Earth, or right at the North Celestial Pole, if you can find Polaris in the sky and drop straight down to the horizon, it indicates the direction of true north. What we mean by true north is not compass north. If you use a compass, it'll actually take you to a place that is not the North Pole, because a compass uses the magnetic field of the Earth. But Polaris will take you to true north, or the point where the Earth is physically turning on its axis. So it is called the North Star because it indicates the direction of true north. And if you were out somewhere, if you were stranded somewhere and you didn't have modern technology, GPS technology, and you wanted to know north, south, east, and west, all you have to do is find Polaris, drop straight down, indicates the direction of north, and then now we know east is this way, west is this way, and in this picture, south would be behind us. So it's a very important thing that Polaris tells us the direction of true north. Many navigators on the Earth, hundreds or thousands of years ago, used this piece of information to help them figure out where they were. And you can make the argument that we would not have explored the surface of the Earth to the degree that we have if it weren't for this one particular coincidence. Now, the other thing that Polaris does for us has to do with a definition that we have to first introduce. And the word is altitude. The usage of this word is not quite the same as you might have heard before. In this case, the definition of altitude is how far above the horizon an object is seen in the sky. So imagine that you're standing out in the field. Here is your horizon all the way around, our imaginary dome of the sky. And let's say there's an object in the sky. Altitude is how far above the horizon the object appears in the sky. And by definition, an altitude of 0 is the horizon, and an altitude of 90 is directly overhead. So 0 is the horizon, 90, and then back down to 0 again. You can't ever have anything greater than 90 or anything less than 0. So the altitude of an object is how far or how high above the horizon it is seen in the sky from your location. Now, the reason why that's critical is because if you can find Polaris, and if you can measure the altitude of Polaris, because Polaris is the point that is the North Celestial Pole, or that point that is directly over the North Pole of the Earth, turns out that the altitude of Polaris is equal to the observer's latitude. So what that means is, if you're outside and you notice that Polaris is, let's say, 25 degrees above the horizon, your latitude is 25 degrees north of the equator. If you're outside and Polaris is directly overhead, then therefore it is an altitude of 90, and so your latitude is 90. And if your latitude is 90, you are at the North Pole of the Earth. If Polaris has an altitude of 0, meaning it's on the horizon, then your latitude is 0, and a latitude of 0 is the equator. So it's really quite usable and quite helpful that the altitude of Polaris is equal to your latitude. So what the ancient mariners on the oceans would do, or travelers on land would do, is each and every day, or each and every night I should say, they would go outside, they would measure the position of Polaris and measure its altitude. That would tell them the direction of north, south, east, and west, but it would also tell them their latitude. So when we call Polaris the North Star, there are two basic things that it'll tell us: the position of true north, as well as the altitude equaling the latitude of the observer. Now, all of this leads us to the notion of what we call diurnal motion. Diurnal motion, the word diurnal means daily. It's similar to the word nocturnal. You probably have heard the word nocturnal before, which means nightly. Diurnal means daily, but in astronomy we use it in a slightly different way. When we say daily, what we are referring to is over the course of a calendar day. So over the course of an entire calendar day, diurnal. Diurnal motion, by definition, is the apparent daily motion of celestial objects from east to west. Now, if we go to the globe here, I'll show you a couple of things that are related to this. If you were to stand on the earth and look at the sky, what you will have is the appearance that the sky is moving over a period of time. In reality, the sky is not moving. What is happening is the earth is turning. And so as the earth turns on its axis, what's going to happen is the rotation of the earth is in the direction of west towards east. So the way that I'm spinning it here on the desk is the rotation of the earth on its axis. However, because you don't feel the movement of the earth, even though the earth is turning, the illusion is that you're standing still, but it's the sky that's going the opposite direction. So in reality, the earth is turning, but you don't notice that. The sky is the thing that appears to turn. Because the earth is moving in this direction, the sky is going to appear to go in this direction. And so what that means is everything you see in the sky has to rise in the east and set in the west. The sun rises in the east, sets in the west. The moon rises in the east, sets in the west. Everything has to move from the eastern horizon to the western horizon because of the earth moving west towards east. So this movement of the earth on its axis creates the illusion that everything is moving across the sky, when in reality it's the earth that's doing the turning. So the idea is the earth is turning west towards east, but creates the illusion that the sky moves east towards west. Sometimes we call this the merry-go-round effect, the illusion that something else is moving around you when you are actually doing the movement. Now, the last little part of this is in this section, we're going to, and in future sections, we're going to continually compare and contrast the ideas of revolution and rotation. And this is an important point where we need to stop and make sure that we get this point at least figured out and solidified. So let's talk about the two. The word revolution in this context is referring to something physically moving around something else. When something is revolving, it is moving through space around another body. Think of the Earth orbiting around the sun. That would be the Earth's revolution. Or the moon moving around the Earth. That would be the moon's revolution. So revolving is the same as moving around another body. Rotation, on the other hand, means something that is turning in place, something that is turning on an axis. So the Earth has this rotational movement to it, spinning on its axis. And unfortunately, people interchange the two words as if they mean the same thing. They say revolution when they meant rotation, or vice versa. So one way that we help people at least make sure that that confusion doesn't occur is let's use some substitute words. Instead of revolution or revolve, you can say orbit. The Earth revolves around the sun, or the Earth orbits around the sun. Instead of rotation, we can say the word spin. The Earth rotates on its axis, or it spins on its axis, and that way you can keep those two at least clear, and there's clarification between the two. In reality, both are happening simultaneously. The Earth is rotating on its axis while it is revolving around the sun. And so it is the combination of both motions that creates the illusion of things moving across the sky. But it's very critical that you keep the two ideas separate. Make sure you say and mean revolution when it's necessary, and make sure that you say and mean rotation when it's necessary. Otherwise, ideas get kind of tangled up, and it's hard to separate the two. Now, we're just about out of time. In the next segment, what we're going to do is show how the rotation of the Earth, as well as its revolution around the sun, creates the appearance of how things appear to move across the sky. But we'll take care of that in the next segment. I hope you'll join me.